I am Jo van Bulk from the IMEC research group at KU Leuven, and I'm going to present our work on LVI, short for Load Value Injection. This was a collaboration with the other people on the slide, and LVI stands for a new class of transient execution attacks. So we have seen many of those over the last 2 years. It all started with Spectre and Meltdown, and then we have seen an entire new wave of attacks including Foreshadow, Zombie Load, Riddle, Fallout, and many other variants listed on this slide. So this sort of wild growth has led to a very entangled and confusing situation with many different research tracks. And in this respect, one of the main contributions of LVI is that we provide a fundamentally new view on some of those existing tracks. So in the paper we illustrate this view by means of a symmetrical square that is cut into 4 pieces. And that's also the way I will organize this presentation. So we will sort of do a sweep through this research field, starting from branch prediction attacks to Spectre, to Meltdown and Friends, and ultimately our contribution LVI. So I will have to say just a little bit about traditional branch prediction side channels. And the key idea here is that modern processors execute instructions ahead of time by means of pipelining, where different execution stages of subsequent instructions are parallelized. And this works beautiful. This works very well until you encounter a conditional branch. At that point, the instruction stream is no longer linear and the processor may have difficulties figuring out which is the next instruction that needs to be fetched. And the easiest way to deal with this is to simply stall the pipeline, to insert bubbles until the branch has been resolved, and then to start fetching the next instruction. The problem with that, of course, is that it will affect performance, and especially on deep modern out-of-order pipelines, processors will try to make an educated guess about where control flow is going so as to avoid these types of pipeline bubbles. Now, of course, every beautiful optimization also comes with a side channel, and that's being depicted on this slide. So we have 2 protection domains, the victim one in green and the attacker one in red. They share the same underlying processor, and that means that while the victim is executing, the processor will accumulate branch prediction history in some hidden microarchitectural buffer, which then later is used when executing in the attacker domain to predict that branch. Now we have an interesting situation here where the execution time of the attacker branch depends on whether that prediction was correct or not, which depends in turn on the branch prediction history trained by the execution of the victim. So the attacker can use it as a side channel to learn certain secrets processed by the victim. And that's in a nutshell what traditional branch prediction side channel attacks are trying to do. Now, to understand the next square, Spectre, we need a new idea. So let's see where we can get that.
Is there a way we can do something like that by injection inside or?
So injection, it turns out that this actually works. So from a somewhat simplified view, Spectre turns around prior branch prediction side channel attacks by starting from the perspective of the attacker. So in this case, we are no longer interested in extracting secret-dependent patterns from the branch prediction history, but we will instead inject deliberately wrong predictions into the shared microarchitectural state. And then at some point when the victim executes, it will misspeculate based on the poisoned history injected by the attacker. So why is that a problem? Well, you can see here on the left a very simple what we call Spectre gadget. So a piece of code that starts with a security sensitive if branch. And the objective here is very clear, make sure that array indices always stay inside bounds. However, after mistraining the branch prediction history, the attacker succeeds in speculatively, transiently executing that if branch with an out-of-bound index. And I say here transient because it concerns instructions ahead in the pipeline that will eventually be discarded when the processor catches up and realizes that this was a wrong prediction. However, by that time, damage may already have been done, as you can see on the next line, because here the out-of-bound secret value is used in a lookup table, which may leak through, for instance, a cache-based side channel. So the main gist here, the takeaway for Spectre, is that processors execute transiently among unintended code paths. and that these unintended code snippets, called gadgets, may be abused as confused deputies to encode victim secrets in the shared microarchitectural state. Now, on to Meltdown, this third square. So Meltdown is much more of a direct violation. We read kernel memory, which is the equivalent of breaking into a building. And the processor is of course not entirely stupid, and this is not allowed. So in the analogy, a guard is walking around and will kick you out of the building after some time. Before that, however, we encode the unauthorized kernel memory in these yellow transient instructions through a cache-based sidechain. So at some point the processor catches up and realizes that this was never allowed to happen, and at that point, however, the damage has been done and we can recover the secret through our cache-based sidechain. This is the main idea of Melta, and a lot of research has happened in this area since. So I want to highlight two main tendencies. One is related to address dependencies. So the original Meltdown attack reads kernel memory inside the current virtual address space. And with Foreshadow, we first generalized this to the physical address space. So we showed that you can break out of your current virtual address space by transiently reading unauthorized arbitrary physical memory locations. The second generalization happened with this recent wave of microarchitectural data sampling attacks, attacks like Fallout, Riddle, Zombie Load, which similarly show that this address dependency can be further relaxed to read completely unrelated data with only a partial address match. This brings me to the second point, which is related to the microarchitectural buffers that serve this data. And without going into details, it suffices to say that the original Meltdown and Foreshadow attacks read from relatively well understood structure, namely the L1 data cache, whereas later attacks, microarchitectural data sampling attacks, read data from more exotic buffers like load ports, store buffers, and line full buffers. So the takeaway here is that, at least on affected processors, mainly Intel processors, faulting loads will transiently forward unrelated, unauthorized data from a variety of microarchitectural buffers. And that's also the starting point for our research. So as you can see from the symmetry, we will fill in this last square using techniques from both Spectre and Meltdown, and we call this load value injection, or LVI in short. Let me start by illustrating the basic idea. So LVI starts from the perspective of the victim, where first some value A is brought into some microarchitectural buffer closer to the processor, let's say the L1 data cache. This happens all the time. At some point later, the victim dereferences a pointer P, which however is faulty. So this faulting load, as we know, the Meltdown effect kicks in, and this faulting load will be served with a completely unrelated value A instead of the trusted value. This value A is then forwarded to the transient gadget instructions following the faulting load in the victim, which may subsequently redirect control flow or data flow based on the value A instead of B. So that's why we call this load value injection. To say the obvious, this is of course only a transient effect, and later at some point the processor will determine that this should not have happened and replay the faulting load and all of its dependent operations once the fault has been resolved. So one thing you might be wondering about is how do you provoke page faults? These are normally rare events that are definitely not under attacker control. So here I have to say something about trusted execution, and more specifically the software guard extensions SGX in recent Intel processors. And what it comes down to from a high level is that SGX offers this notion of enclaves, which are confidentiality and integrity protected by the CPU itself using encryption and hardware level isolation. So that means the operating system is untrusted and we can provoke page faults in a trivial way. To go a bit more into specifics, SGX implements an additional level of access control checks after the legacy page table based address translation, which means that we can shortcut this process as an untrusted operating system adversary and trivially provoke page faults for enclave loads. So the takeaway is we have a primitive to arbitrarily provoke page faults for trusted enclave loads. Okay, so let's see what can go wrong in practice. This is a very simple toy example. The most important line of code is the highlighted one, where we have a pointer-to-pointer dereference. That's also being illustrated on the right with these yellow boxes. So we have a trusted pointer which points to a trusted index, which then is used inside an array. Of course, through cache timing attacks, we can see the value of the trusted index, but we don't care because it's a public value anyway. However, what goes wrong is when we do our page table trick and we provoke a page fault on this trusted pointer dereference, then the meltdown effect kicks in and an unrelated value, in this case the untrusted argument accessed by the victim earlier, will be injected into the transient data stream, and this allows the attacker to point to a secret and encode that in the array. So this gives you an arbitrary read primitive to see how that works. We have here a flush reload sweep over this array, and you clearly see two dips here, right? One corresponding to the D, the dummy transmission intended by the victim, and one corresponding to the S, the secret injected by the attacker. So the beautiful thing is that this works for a variety of different microarchitectural buffers and a variety of different microarchitectural faults. So in the paper we contribute an extensible taxonomy to reason about LVI variants, more on that in the paper. Another cool thing, of course, is that this is by no means limited to data-only attacks, and you can do also all kind of control flow hijacking attacks in the transient domain. This is being illustrated on this slide. Again, the first phase loads some attacker value into the microarchitectural buffer, and then a bit later the victim enclave executes an indirect branch operation that can be a jump, a call, or a return, which loads the branch target address from trusted enclave memory. Now, the trick is to make that return fault, so we revoke access rights on the enclave stack, which triggers the meltdown effect for faulting loads and replaces the trusted value, the trusted return address, with whatever value that happens to be present in the microarchitectural buffer close to the processor. So this essentially allows the attacker to inject arbitrary return addresses and hijack transient control flow, much like in a traditional return-oriented programming hop attack. So we can go to all kinds of gadgets and encode secrets. So you can see that in action here. This is the victim code. You see the value R being loaded into some register and then encoded over a covered channel. This is the attacker code, and you can clearly see the page table manipulation prior to entering the victim. Now, this is the attack in action, and you can clearly see that the victim control flow is being hijacked and the value R, some supposed secret, is being encoded over the covered channel. Now, you might be wondering, do recent Intel processors not have silicon level patches against meltdown? Is this even relevant for these processors? And the answer is surprisingly yes. We found that the patches for meltdown merely replace the data for a faulting kernel load with 0, which means that the value 0 is still forwarded to transient dependent operations, and we argue in the paper that 0 is by no means a safe value. So one of the things we show, for instance, is that transient null pointer dereferences go outside of the enclave, and the value null is a valid virtual address where we can map an attacker controlled page. So that means that, for instance, for pointer to pointers, we can completely hijack the result of that trusted operation by the first level going to the 0 page out of the enclave, putting arbitrary data there, and then again injecting that as a second level of that double pointer dereference. Time to say something about mitigations. How can we defend against these attacks? Well, the most important point to make here is that merely flushing of microarchitectural buffers on enclave entry and exit is not anymore sufficient, and this represents a true paradigm shift in the way we should think about defending against meltdown type illegal transient forwarding. So we also engaged in a very lengthy embargo period with Intel, almost a year, to come up with new types of mitigations. How does that look like? Well, this is the general scheme of a load value injection attack, right? And what we do is to insert an L fence to stall the processor pipeline in between every potentially vulnerable load and potential gadget. So that's literally putting a fence to stop that load value injection from happening. That reminds a bit to the mitigations widely deployed in response to Spectre v1, but an important difference here is that we can hijack potentially every memory load operation. That's a lot more widespread than conditional branches, and also for indirect branches in contrast to Spectre v2, we do not need to poison specific microarchitectural buffers that can be flushed, and hence those indirect branches have to be serialized as well, as you can see below. That even requires blacklisting widely used instructions like the x86 red instruction and then rewriting that at least. So also to illustrate this point, the Intel quoting enclave, crucial enclave signed by Intel, had 23 manually inserted fences with surgical precision before LVI, and then after mitigations became public, we counted almost 50,000 fences in that binary. So that's a true march of the L fences. And the performance overheads are, of course, to be expected very, very high. We, in the paper, described our own prototype mitigation, which reports over 900% overhead for some benchmarks in OpenSSL. We also tested the mitigations that Intel deployed production for GCC and a more optimized version for Clang LLVM. And for OpenSSL, you see comparable numbers. We also did that for Spec, where you see that it depends really on the application, and also that optimized mitigation from Intel for LLVM does pay off. The people from Phoronix also interestingly did some independent analysis after our results became public in March, which confirms these numbers. In summary, we presented LVI, a novel gadget-driven technique to reversely exploit meltdown-type effects. On the short term, LVI really necessitates extensive LFENCE compiler mitigations, at least for Intel SGX enclaves. We also discuss a bit of non-SGX impact in the paper, but that remains mainly academic for now. On the longer term, we believe that LVI really underlines the importance of improved silicon-level mitigations for newer CPUs. That's a tendency that's already going on. And then finally, we refer to our website lviattack.eu for more information.